Hello, welcome to a new lesson. And today we are going to introduce a new course on the channel that is going to be about thermodynamics. So, we are going to start this course by speaking about the entropy of the ideal gas. This is because I do not want to start exactly from the basic concepts of thermodynamics because I think that there is already a lot of content in YouTube speaking about these topics. For example, the equation of the ideal gas, right? So we are going to take some of these basic results into these lessons and work with them a little bit to show some more, just a little bit advanced results from thermodynamics. Okay, so that's why we want to start already with the concept of entropy. And we are going to use again the ideal gas to see what does this mean. Okay, so just to recall, the ideal gas is a set of particles or molecules that it has the property that each molecule that composes the gas is going to be a constant kinetic energy. Okay, so if there are collisions in this system, these particles do not change their velocity on time. Okay, so that means that there is no energy loss from friction, for example. Okay, and in this example, we are going to define entropy of this gas by taking into consideration that the number of particles is going to be constant. Okay, so that is going to be important to recall. And that number of particles, it is often named with the letter n. Okay, so that means that if n is constant, the n is going to be equal to 0. Okay, the change on n. Okay, perfect. So how are we going to start? We are going to introduce the two main equations from the ideal gas. The first one stays for U equals 3 halves and kT. And the other one is P times B equals NKT. Okay, so we are going to inspectionate just a little bit these two expressions. For now, we are not going to show, but you should know that this element, K times T, it is proportional to the total kinetic energy of the system. Okay, so it is very easy to conclude that the total kinetic energy, which is the sum of the kinetic energies from each particle, it has to be proportional to the total internal energy of the system. Looking at, it is an ideal gas, the internal energy is going to be obviously related with the kinetic energy of each particle. And look that we are multiplicating by the number n, which is, the number of particles. So this is something like taking the kinetic energy of each particle and then multiply it by the number of particles to get the total energy of the system, which is, just something that we should expect that is true. Okay, so the other equation just tells us that the product between the pressure and the volume is equal to the number of particles times some constant that is associated to just ideal gases and the temperature of the gas. In this case, this formula is valid for a specific moment in time, right? If we calculate the pressure, the volume, and the temperature on a certain time, let's say t0, that means that this product is going to, this equation is going to hold. Okay, so with this, we can work a little bit to define the entropy of this system that we have here. Okay, so we're going to start by talking about the concept of internal energy. So as we mentioned, the internal energy is like a measure of the total kinetic energy of each particle of the system. And it's going to be important to recall that this internal energy is going to be a function of the entropy, the volume, and the number of particles. Okay, this is going to be very important because we are going to consider this as natural variables, okay? Later on, we will see that, well, the internal energy can depend on other variables like the pressure or the temperature, of course, but we are going to consider these three variables as the most important variables associated to the internal energy for now. Okay, so if we suppose that the internal energy depends on these three variables, we can calculate the total differential of the internal energy as du equals the partial of u with respect to s, ds plus the partial of u with respect to b, db plus the partial of u with respect to n, dn. And again, from basic thermodynamics, you should know that we often define the temperature as the derivative of the internal energy with respect to the entropy. We define minus the pressure as the derivative of the internal energy with respect to volume. And we define something called as the chemical potential, mu, equals the partial of u with respect to n. Okay? Something that we can say about this chemical potential is that, well, it is associated to each species that composes the ideal gas. I mean that, well, the nature of each particle can be different, okay? But for now, we are going to consider that all these particles are made of the same element, okay? So we just have a monatomic gas in this case. If we do not have a monatomic gas, I mean that we will have many chemical potentials, mu sub 1, mu sub 2, all the way up to mu sub n, where n will be the total number of species that composes the ideal gas. Okay, so with this, we can say that the total differential of the internal energy is equal to TdS minus PdV and then plus mu dn. But looking that we said that on time, the number of particles is not going to change. Dn is going to be equal to 0, meaning that du is equal to T ds minus p dV. And remember that what we wanted to find is an expression for the entropy of the ideal gas. So that means that if we solve this for ds, we will have that 1 divided by T du plus p divided by T dV is equal to this. Okay, so with this, we can say that, well, we may need to integrate this equation to find what is S. Okay, but how are we going to do that? Well, to integrate this, we may be interested in having here maybe not a differential of u or an element of u, but instead maybe we need to have something like dt, right? Because we have here the variable t. So if we are able to express this as something times dt, then we will be able to take an integral here, and something similar happens here. So that's why we are going to use these two equations that we mentioned at the beginning of the lesson. So it is very easy to see that from this first equation, if we take the differential of u, well, that is going to be equal to 3/2 nk dt, right? Because n and k are constants. So we have that du is equal to 3 divided by 2 nk dt. And from here, notice that we are interested in the quantity p divided by t. So it is easy to see that, well, that is equal to nk divided by v. Okay, so if we take these results into the ds expression, we will get 1 divided by t, 3 divided by 2 nk dt, and then plus p divided by t, which is nk divided by v, and then dv. Okay, so perfect. So in this case, we will need to take the integral on both sides of the equation. But how are we going to do this? Well, we need to establish something. First of all, we should notice that the result that we are going to get is a function of the temperature and the volume, right? Yeah, so we are going to get an entropy that depends on the temperature and the volume. So that means that on time, we are going to get from an initial state of entropy, let's call it S sub 0, which is going to depend on an initial temperature and on an initial volume, like this, and we are going to finish on a final state of entropy, which is going to be S of t comma b. Okay, so that means that our integral on the S is going to be from this state to this other state. And well, that same thing happens with the temperature and the volume. I mean that the change on temperature is going to be from an initial state of temperature T naught, and the final state is going to be on a temperature T. So in integral terms, it's going to be something like this. We are going to get the integral from the initial state of entropy S sub 0 to the final state of the S. And then this is going to be, well, 3 over 2 and k, the integral from t0 to t of dt divided by t. And then plus and k, the integral from the initial volume to a final volume b, db divided by b. So yeah, I think this is very easy to solve because they are really easy integrals. So this is going to be S minus S0, which recall that S0 is just the entropy evaluated at the initial conditions T0 and B0. So we can say that this is S0 of T0 comma B0, and then equals to 3/2 and k, the natural log of T from T0 to T, and then plus nk, the natural log of B from B0 to B. Okay, so what is this going to be? Well, for example, if we examine this expression, we will get something like 3 divided by 2 nk, the natural log of T, minus the natural log of t0, right? But for logarithmic properties, we can see this as the natural log of t divided by t0. And something similar is going to happen here, right? This will be plus nk, the natural log of b divided by b0. So if we take these 3/2 here to the exponent of the logarithm and factor the nk, we will get nk, the natural log of t divided by t0 to the 3/2, and then plus the natural log of b divided by b0. Okay, so this is going to be nk, and for logarithmic properties, this is going to be the natural log of, well, t divided by t0 to the 3/2 that multiplies b divided by b0. Okay, let me put some brackets here and recall that this is equal to the entropy evaluated at t comma b minus the entropy evaluated at t0 comma b0. Okay, perfect. With this, we can see that the entropy increases if the temperature and the volume increase. Okay, so that's like a very first important result. Perfect. So in this case, we have a dependence on the temperature and the volume, but what happens if we are interested maybe in changing that dependence, maybe from temperature and volume to temperature and pressure? How would we do that? Well, it shouldn't be so hard, looking that we have a relation between the volume and the pressure, which is this one, right? So we're going to solve this equation for the volume, and then we are going to take that result into the function S that we found to express it in terms of the pressure. Okay, so from here, we can see that the volume is equal to nkt divided by p. So that means that on the initial conditions, the initial volume is going to be equal to nk, the initial temperature, divided by the initial pressure. Okay, so those are the equations that we are going to use just to express the entropy in terms of the pressure. Okay, so with this, we can change the structure of S, and let me just write S minus S0 for now, to see that this is nk, the natural log of t divided by t0 to the 3/2, and then b. But B is equal to nkt divided by P, right? And then this is divided by V0, which is nkt0 divided by P0. Okay. So, of course, we can simplify these nks to get that this is nk, the natural log of T divided by T0. Well, yeah, let me do it. It is T divided by T0 to the 3 halves, and then T P0 divided by P T0. Okay, so we can take this T divided by T0 into this expression over here to see that this is nk, the natural log of T divided by T0 to the 5 halves, and then P0 divided by P. Recall that on the volume expression, we had the variable V here at the numerator, but in this case, we have the pressure dividing this initial pressure over here, like at the denominator, right? So that's an important difference. Okay, so with this, we can say that, well, this is the expression for the entropy evaluated at the temperature T and the pressure P minus the initial entropy evaluated at the initial temperature and the initial pressure. Perfect. So yeah, this is already an important result for the entropy, well, in terms of the temperature and the pressure. Okay, so with this, we could say that the entropy evaluated at T and P is going to be, well, this quantity, right? It's S0, T0, P0, which is a constant that depends on the initial conditions, plus nk, the natural log of T divided by T0 to the 5 halves, P0 divided by P, like this. We should point out something. The entropy is an extensive property of the ideal gas. What does that mean? I mean that if we have an ideal gas, for example, like this, and we split this ideal gas into 2 halves, the entropy is going to be divided by 2. I mean that the entropy of the halves of the ideal gas is going to be S divided by 2 on each side of the gas. Okay, so what this thing means is that, well, the entropy depends on the quantity of matter that composes the gas. Okay, this is something similar as the volume, right? If we have a box, a cube box like this, that it also contains a gas, right? If we want to calculate the volume, well, we will have some value B, right? But if we split this cube on 2 halves, well, we will get that the volume is going to be divided by 2, right? I mean that the volume changes if we split the quantity of matter that composes the gas. That is what it means to be an extensive property. So, in conclusion, we can say that the entropy is proportional to the quantity of matter. So that means that this quantity that we have here is going to be proportional. Well, yeah, it's a quantity that has as a factor, well, the number n, right? So, because n is the quantity of particles. So that means that the entropy at the end, evaluated at T and P, is going to be something of the form n times k that multiplies some other quantity that refers to the initial conditions of the entropy that we are going to still name as S0, but it is a different quantity, right, from this, evaluated at T0 and P0, and then plus the natural log of T divided by T0 raised to the 5 halves, and then P0P, like this, okay? This is just to express that the entropy depends on the quantity of particles, right? And the dependence is because the entropy is directly proportional to the quantity of matter that composes the ideal gas. Okay, so yeah, I think we can see this as the final result of the lesson is just a function, yeah, which we name as entropy, that depends on the temperature and the pressure, right? That is an extensive property of the ideal gas. So for now, this is going to be the expression for the entropy of the ideal gas. So after saying this, we cannot say that the entropy is only a function of the temperature and the pressure, right? We are watching here that it depends on the quantity of particles. We said at the beginning that, well, the number of particles is going to be constant, right? And in that case, we showed this expression. Okay, so that is valid for that case. But the thing here is that this final expression that we found is going to be valid even if the number of particles change. So we can see this as a function of entropy S of the variables T, P, and N. Perfect. So with this, I think I should finish the lesson here. That is going to be the final result. Perfect. I hope you enjoyed this first lesson of thermodynamics on the channel. And thank you so much for watching.